Distances. Stopping distance depends on what?
Force.
In fact, you have stopping and braking. Stopping distance depends on thinking plus braking. Okay? Things or factors that can affect your thinking time, the distance that you take before you've even thought about it, is your reactions, yeah? You can speed up your thinking time, for example, if you're drinking stimulants such as coffee, energy drinks, things like that. Or you can slow down your reaction time by having different things, being very tired, yeah? Taking drugs that slow your processes down, your thinking time down, okay? Braking distances, dependent on weather, the tyres that you have, so you may not have maintained your tyres, the road surfaces, for example, if it's a nice smooth tarmac road, fine. If you're driving on gravel or stones, for example, it might be a lot harder to brake. Okay, so the distance it takes you to stop will be a part of your thinking and your braking. Now, one thing that they could ask you about braking, okay, if you're traveling at a specific speed, you may have a kinetic energy, or you will have a kinetic energy, okay, of around 1500 joules, let's say, right? And then what they could say is, you're traveling at this speed, your kinetic energy is this, the car brakes. Now it says the distance taken to brake could be 25 meters. Calculate the force that the brakes applied to the wheels, yeah? What force was coming from the brake? This kinetic energy is transferred as a work done. So the work done by the brakes equals the force of the brakes times the distance. The kinetic energy is the work done. All the kinetic energy that you had in your car as you were moving, which then came to a stop, has been transferred by work done, force on the brakes. That will be dissipated as heat into the surroundings, okay? So I have my work done, which is 1500. I know my distance is 25, so F is what I'm looking for. So if I want to find F, 1500 divided by 25 gives me 60. You got 100, so it'll be 4, 40, 60.
So much as on the
60 newtons. Okay? Check it, because that might be wrong, I'm pretty sure it's right. And that's pretty much it, yeah? So again, they could have given you distance and force. They could have said the force from the brakes is 1.2 kilonewtons, so there's a conversion there of kilo, okay? 1.2 kilonewtons. The distance travelled before the car stops could be 60 meters. What is the work done by the brakes, yeah? Work done is the force of the brakes times the distance it takes to stop, alright? So that's braking distance, okay? We've also had work done in chapter SP8 as well, so they could ask you in both. Circular motion. Object travelling in a circle. Examples could be the moon around the earth around the sun, any bodies in space that are orbiting around something else, usually travel in a circle, not perfect, but rough. And there must be a force which we call centripetal force, acting towards the center, okay? It has to be towards the center, hence the name, towards center, okay? Possible centripetal forces, gravity, friction. Example of where friction is a centripetal force. If the train is moving around in a circle, then yes. A car driving around a roundabout, for example, the tyres and the road would create friction towards the centre of the roundabout, so it goes in a circle. Or tension. Now, tension could be in a string or a rope, generally, okay, or a cable, if you're swinging something around in a circle on a rope. It could be possible examples are like fairground rides, where you're in, it's kind of connected to a string, and then the fairground ride goes around and you move outwards slightly. Or even literally, if a person, like the ice skaters that we've seen before, If two ice skaters are on the ice and one of them is holding the other and spinning them round in a circle, the tension in the arm, which is pulling you into the circle, is your centripetal force. Okay? So centripetal force acts towards the center. It goes from the object directly towards the center. Alright, we've seen that in the example with one mark. The object, however, travels around the circle in that direction. It's moving around in a circle because there is a velocity which is at a tangent. So you have a velocity at a tangent to the circle, okay, or 90 degrees to the centripetal force. All right. Now, possible questions could be: if the centripetal force disappears, for example, if you're an ice skater pulling someone around in a circle and you let go, there is no longer a centripetal force. In what direction does this person move?
Last direction.
They will move in a straight line, perpendicular to the centripetal force, or in a straight line at a tangent to the circle. Okay? Other things we need to consider. The tangential velocity, is it constant or is it changing? Why?
Because it's changing that distance.
Exactly. Velocity, constant speed, but constant change in direction means that the velocity is changing, and if the velocity is changing, we know that changing velocity is an acceleration. So the object is always accelerating. Okay? So because velocity is a vector, not only does size matter, where speed could be 15 meters per second, in the whole circle the speed would always be 15, right? But because the direction of the object is changing, if you move in a circle, you have to keep changing your direction. Because it's a vector, the direction changes, so the velocity changes. Speed is constant, but velocity changes, and if velocity changes, it must have an acceleration. The acceleration is also towards the center of the circle, okay? And we call that also centripetal acceleration. Alright? And the only other thing in topic 2 is the practical.